since we haven't met, I'm going to steal from Robert Rice in the Power Hungry podcast and say, imagine that you have 60 seconds to introduce yourself to a room of strangers. Why don't you do it?
So the first thing I will say is that I'm a space technology enthusiast and particularly interested in space technology related to microgravity conditions, right? So low gravity science and technology development. I lead a laboratory at Georgia Tech with over 40 students, and we create what we believe are going to be some of the most critical technologies for the next 30 or to 50 years. We're interested in what happens at the surface of the moon, what happens at the surface of Mars, and what happens in the microgravity environment that you experience when a spacecraft is orbiting the Earth. So what you're going to see today is half of what we call microgravity research, because the other half is biology research, which doubts a little bit, but it's not really our field of expertise. We work with fluids in space. That is our core expertise area.
Excellent. Okay. And maybe just another 30, 40 seconds about your background.
So I was born in Spain. I'm a Spanish citizen, and I came to the US in 2019 as a PhD student to the University of Colorado Boulder. I picked up there the passion for skiing, hiking, and camping, which I bet many in this call share. My wife lives with me here in Atlanta. We moved last year when I started my position at Georgia Tech. And I also played the piano since I was 5. So in fact, my come to Jesus moment was when I made 18 after high school. I had to choose between playing the piano or becoming an engineer. I guess my artistic self didn't win that battle, but I still play the piano nowadays. I have a baby grand at home, and that is my roommate. So yeah.
Okay, that was perfect. Maybe if we run out of things to talk about, you can give us a recital, but I suspect that's not going to happen today. You have some slides prepared, hopefully within, say, 30 minutes. Presentation time. Why don't you just start on that?
That sounds good to me. Let me see. It's 4:07, so 4:37. Okay, we can make that. Let me share my screen now. Here we go. First of all, I would like to welcome you all for your kind invitation to present today here at the Foresight Institute. One of my students is related to your organization, Romain Fontaine, and he told me about you first than anyone, right? It is a big honor to be presenting here today. As I mentioned before, I'm an aerospace engineer interested in space technology. What my laboratory does is low gravity fluid mechanics, mainly, together with many other things that I will discuss today. First of all, as I mentioned before, I was born in Spain. I studied in Seville, in Politecnico di Milano, also in Italy, and then in 2018 I came to the US, to the beautiful Boulder in Colorado. Finally, I ended up in Atlanta, where I started my professorship last year. I'm an assistant professor. I will go up for tenure in 4 or 5 years. Until then, I'm basically having a lot of fun.
Sorry about that.
No worries. About my hobbies, as I mentioned before, I love skiing and I love hiking. Colorado has a lot to do with it. Right now, I'm in this other place. It's a big city, Atlanta. We are in the last ranking. I think we are the second best aerospace engineering school in the US, first among public universities, and Georgia Tech is the third university in the whole country, right? So it's a very good school. That rankings don't mean a lot to me. They mean that we get good students, right? And really the breadth of research and the intellectual, all the students that we have the pleasure to work with here is just outstanding, right? Exemplified by their high productivity and their high qualifications when they can come out of here to the industry, to the space industry. My office is right here in front of Tech Tower. I guess I'm lucky in some sense. Our building is pretty old, but otherwise it's a pretty good place to be. Let me start the presentation by talking about things that you know very well, okay? Last year in November, the SLS had the first real launch after tests, right? And the image that we get in our minds is this wonderful, powerful rocket or launcher getting off of Cape Canaveral, right? With this huge amount of power being released per second, right? There is something that you don't see in this image that is not obvious, right? Which is the amount of propellant that is inside these tanks, in the liquid propellant tanks, right? Sloshing in launch stages has been a critical concern for space engineers since the beginning of the space age, right? It is one of those fluid mechanics progress that has a direct and very obvious incident into space technology development, but it is not the only one.
Alvaro, just sorry to interrupt for a moment. I want to just say that slowly for people in case they missed it. Say that slowly about sloshing.
Okay, of course. So sloshing is the random movement of liquids in partially filled containers, right? Sloshing has been a problem for space engineers since the beginning of the space age. because sloshing can alter the dynamics of a launcher or any space vehicle in general, right? Since the very beginning of the development of space launchers, fluid mechanics has been a core element of everything that we have done in the space sector. But it is not the only element. Right now, we are dealing with some of the biggest sloshing elements in space, like the SLS, right? But it is not the only thing we care about. Chandrayaan-3 recently landed at the south pole of the moon. We are very interested in the south pole of the moon because that is a location where we can find water. When you split water into hydrogen and oxygen through an electrolysis reaction, what you get is basically a pair of a propellant and an oxidizer, right? That can be used in deep space to propel your spacecraft. If we are able to leverage the resources located in the south pole of the moon, we will basically get a gas station on our way to Mars or to any other destination in the solar system, right? The Starship concept, at least one of them, involves refueling in low Earth orbit, right? We are considering the possibility of establishing permanent human presence at the surface of the moon. Water and the recycling of water through environmental control and life support systems is going to be critical for basically every human habitation system that we develop for the surface of the moon or any other planet. Again, we are dealing with fluids, but fluids in this case in a very particular domain, in low gravity conditions. So again and again, we are dealing with a particular state of matter, liquids, right? And liquids and gases, mixed in particular. In this other example, lunar flagship that was designed by JPL in collaboration with Professor Glenn Lightsey here at Georgia Tech and others, was mapping the presence of water at the south pole of the moon. But Flashlight itself was dealing with propellants inside a very particular conformal tank geometry, inside the limited volume and space available in a CubeSat. Again, over and over again, we see that fluids play a key role in space exploration and in space technology in particular. Our laboratory is highly interested in what happens with fluids when you either remove the effects of gravity or diminish them to the point that you enter what is called a low gravity regime. And that is what we are going to talk about today. First things first, what is microgravity? This question, I ask this question to my senior design students every semester, and it takes 5 to 10 minutes for them to figure out the exact definition of microgravity. When I say students, I mention professors, experts in the industry, and basically everyone who is not specifically working in this field. I think that the reason for that is that we are very accustomed to images and videos like the ones that you can see in the screen, right? We are accustomed to seeing people floating in space at the International Space Station or any other orbiting mission. So for us, this has become natural. But when the space age began in the 1960s, this was far from obvious, right? This was not something that you could see every day. So if we're looking for a definition of microgravity, let's go to the dictionary, right? Let's go to the open sources and let's see what others say about microgravity out there. If we take a look at this space.com article, we can say we see the paragraph that is highlighted here, okay? While space isn't completely free of the effect of gravity, especially immediately around Earth, this fundamental force is much weaker in orbit than on the surface of the planet. And they mention later on that gravity is 90% weaker at the ISS than on terra firma. I have to say absolutely nothing correct about this, right? And it is an absolutely wrong definition for a variety of reasons, right? First of all, gravity doesn't disappear. The definition of microgravity is not the disappearance of gravity. It is a condition of free fall, as we will see in a second, right? And there is another reason why this is wrong. For the gravity force, as we understand gravity, at the ISS is 90% of that on Earth, not 10%. So you may say, okay, maybe this is just a wrong definition, it can be a mistake. But if you go to the Oxford Dictionary or to Google, you find that the definition of microgravity is very weak gravity, as in an orbiting spacecraft. Or if you want to get fancy and go to ChatGPT, you will find very similar conceptual mistakes. So let's clarify, first of all, what we mean by microgravity. Imagine that you are in an elevator, right? And you are holding your phone in your hand. Suddenly, the rope of the elevator is cut, and you're in a free fall condition together with your phone. With respect to you, your phone will be levitating in front of you. The reason being that gravity affects both yourself, you as the observer, and the phone that is levitating in front of you in the same manner. If you're familiar with linear kinematics, you will see that the acceleration of the phone with respect to yourself is very close to zero. In other words, when we talk about microgravity, we talk about the condition in which people or objects are in simultaneous free fall. The term micro also implies that relative acceleration between the two objects is of the order of 10 to the minus 6 g0. So this is the actual definition of microgravity. You can experience something close to microgravity when you jump. In that short parabola, you are experiencing a free floating condition, but that lasts for far less than a second, right? In an orbiting spacecraft, an orbiting spacecraft is also a free fall condition, a drop tower, a parabolic flight, etc., right? So this is what we mean by microgravity, not the absence of gravity, not compensated gravity, not the absence of the drag, right? This is the actual definition.
Hey,
So-
one thing that I like to say about it, also
Sure.
a number of different things, but good to see the equivalence principle invoked here, is that so-called zero gravity is not floating. It's not what humans would consider or experience as floating. It's what they would experience as falling.
Yes, there is a big theoretical battle in here, right? I have a friend, Professor Michael Dreyer in Germany, who prefers to use the term compensated gravity, right? Because what we are experiencing as microgravity is the lack of a reaction force. And that is what we call microgravity. The term microgravity was established very early in the space age, but it is not really accurate, right? Because it leads to the confusion that, okay, microgravity has to be the absence of gravity, which is what everyone thinks, or almost everyone thinks, right? And that is not right. Zero gravity is another term for it. It's not a term that I like particularly because zero gravity implies zero, right? And there is almost never a condition in space where you experience zero gravity. The only 2 points or the only type of points where you experience zero gravity, and it is not even true, are the Lagrange points, right? Between the Earth and the Moon, ignoring the other gravitational effects that may be around. So there is not really a zero gravity point in space ever. You have always some sort of level of residual. That is a terminological battle. In a practical sense, I am an engineer. 0.1 plus 1 million is 1 million for us. So that is what we really care about when we design space systems. But yeah, let's move to, if you want, Creon, let's move to low gravity fluid mechanics, okay? We have discussed the concept of microgravity, which is the same for every field. But let me present a case to you, okay? Imagine that you want to drink coffee in space. Turns out that the pleasure of drinking coffee comes mostly from the smell of it, right? Imagine drinking coffee. I encourage you to try this. Drink coffee while you close your nose, right? And drink the mixture. You will see that the sensations are quite different than just having your cup of coffee in the morning. This was a pretty annoying problem at ISS because if you wanted to have an espresso in space, as Samantha Christopher in 2015, you have to use these plastic bags. The reason for using these plastic bags was that if you don't use them, all the liquid spills out, right? And you can generate a big mess. First, Don Petit in a shuttle flight and then Mark Bisloga at Portland State University designed this little gap in here. The shape of this gap is important. This is what we call a wedge geometry. In space, the dynamic of fluids are dominated by capillary forces, right? No gravity, no buoyancy, because we are in a condition of free fall, in a free fall regime. In order to avoid spilling the liquid away in a very consistent movement, as we saw in the previous video, what we do is we use these corner geometries to get the fluid stuck to one side of the tank and leave it free at the other side where we have these ground geometries. You can visualize this. If you take a glass of water and you take a look at the contour of it, you will see a wedge geometry, a little slope. That slope is the capillary force. On Earth, the slope is very small. In space, the slope dominates the whole good behavior of the liquid.
Is the surface tension force so strong that it prevents sloshing in this little cup?
No, it doesn't. It doesn't prevent it. It controls it up to some point, right? There is a good book called Low Gravity Fluid Mechanics by Mishkis. It was written in the 1980s that goes through all the math and the derivations for it. But capillary forces are not strong enough to control the liquid in there or control the sloshing. They damp part of it, but there is always going to be some sort of oscillation, both here and in high gravity conditions. But I'm not so concerned about that at this point. I'm concerned about other problems. Okay, so imagine that you want to celebrate something in space and you open a bottle of champagne and you want to drink champagne in space. The question that I always ask my students, and I'm going to ask you right now, Creon, is this. Can you use this capillary wedge in space to drink champagne? What do you think?
I think that you're going to have a problem with the bubbles messing things up.
In which sense? You're right. You're absolutely right.
Well, there's going to be the gas is going to come out and it's going to not go to the top like it does on Earth in a champagne glass. It's going to just accumulate in random places and it's going to turn it into the foam.
Yep, that's absolutely right. It generates, as you described before, a very big mess. It may seem that drinking champagne in space is not necessary in some senses, right? And I may agree with you on that point.
Unlike drinking espresso in space, which is necessary.
If you work 12 hours per day, I feel that a cup of coffee can help a lot. But if you think about, actually, you cannot drink carbonated drinks in space simply because when they get to your stomach, there is no phase separation. So that is a big mess, right? That can generate a big mess. But this may seem as a secondary problem, and it is from some perspective, right? But it turns out that bubbles and bubble flows in space in general are predominant in a wide variety of applications, from phase separation, which is a very basic process in all sorts of technologies, to hydrogen and oxygen production for in-situ resource utilization or life support, to plant watering systems. So when you want to water a plant in space because there is no buoyancy force acting on the system, the liquid tends to, let's say, coat all the roots of the plant, eventually asphyxiating them. So you need to make sure to provide the right amount of liquid and the right amount of gas to keep the plant alive. So yeah, it is a very complicated mess that happens in there, and it is really challenging to design fluid management devices for space applications. That is why my laboratory focuses on this particular problem. What we do, and this is just a very brief overview, we use the two traditional forces to manage low-gravity fluid mechanics systems, which are inertial and capillary forces, right? But I think that what distinguishes our laboratory is that we add more elements into the mixture. In particular, we include magnetohydrodynamic, electrohydrodynamic, and acoustic forces. And we study a variety of fundamental mathematical problems, which are intrinsically interesting, right? But also a wide variety of applications, like the ones I have just mentioned. So let me cover in the 20-ish minutes that we have remaining some of those applications to show what we really care about here. The first one, because it is the simplest, is going to be phase separation. And here we use an effect that is not very well known because we cannot see it on Earth, which is the magnetic buoyancy effect. Okay, this may come as a surprise to some of you, so some others may be very familiar with this. Okay, but it turns out that every material that you know is, to some extent, magnetic. By magnetic, I mean that it has a response to magnetic fields, in this case, to inhomogeneous magnetic fields. This is a video, an accelerated video from the LGST Lab, a YouTube channel that I do recommend. It has some pretty cool stuff uploaded. They have a piece of wood, which is a very humid material, water and magnetic materials. That means that they are repelled from magnets. We don't see this effect on Earth because, as you can see in this video, the force that we are experiencing is extremely weak. But in space, due to the absence of buoyancy, this force becomes dominant. And that is what makes it so interesting. We can still observe the diamagnetic effect on Earth. Okay, let's say that diamagnetic materials could be conceptualized as the opposite of ferromagnetic materials, or better say, paramagnetic materials, in the sense that they feel repelled and not attracted to magnets or magnetic fields, right? In this case, you can use a huge superconductor to levitate a little frog. If here, you can use a frog or any other organism with water, right? And this superconductor is available at NASA and many other places, right? It is a very old technology, but you require tons and huge amounts of power to make this happen because the magnetic fields that you use are of the order of 17 10, which is absolutely savage for any application. Instead, in the space, we follow a simpler approach. We take just a sample, a container with a liquid, and a small magnet, like the one you can get in your hardware store in the corner. This magnet is an neodymium magnet. It is the stronger or denser technology that you can find nowadays. And we get it close to a syringe with this liquid, a little sample, where we're going to inject air bubbles. We're going to launch this in a classical microgravity facility, the Drop Tower of Bremen. It is a 120-meter vacuum tube owned by the University of Bremen and the CERN Institute. The tube inside looks like this. So we get a capsule that has 500 kilograms, and we catapult the capsule 120 meters high, right? So the capsule is flying from the bottom of this facility to the top. And inside this capsule, we have our experiments. Because the capsule is in a condition of free fall, and we are experiencing microgravity conditions inside of it. The gravity force is acting in the same way in every element inside the capsule. So this is where we run most of our experiments in our lab. What is going to happen, you're going to see it right now. So we're going to inject the gas bubbles in there. And the little magnets are going to attract them, as you can see in the videos, which, by the way, are slowed down. So this happens way faster than you can see in the video. The reason why we can see this in space and not on Earth again is the absence of buoyancy. Even the slightest disturbance becomes dominant in this environment. And you may wonder, okay, these bubbles and these things are pretty cool, right? Okay, nice fundamental science, but what do they care? As a space scientist or as a space technologist, why is this important? Because we're achieving phase separation without moving parts. So this is a fully passive, reliable system. We are doing it without any sort of membranes or expendable mechanisms that consume up mass and up volume, right? And it is also extremely lightweight. So it is fully reusable. It has many competitive advantages for a variety of applications. One of those applications is biology sample experimentation, right? This is Professor Sandy Magnus. She is at Georgia Tech right now. She was a NASA astronaut for 3 times, first at the shuttle, then at the International Space Station. And she's carrying out here some biological sample experimentation. When you deal with biology, as you probably know, you need to provide culture media, LB broth. And this culture media is a liquid. When you deal with liquids in space, you need to manage syringes that insert bubbles into the mixture. And you don't want to have gases into your experiments. For that, you need to use actually quite a bit of filters and centrifuges to get those mixtures separated in space. Many astronauts just take a syringe in their hand and they shake it to generate a centripetal force that brings the liquid to the outer location and the gas to the inlet location, right? It is just a possibility. There are many ways, but in any case, what I want to transfer here is that this is a very annoying process that can be solved in a much simpler way with some of the technologies that we're developing in our lab and many others that other labs across the US are developing as well. Let me cover more from a space technology perspective, what I think is a more interesting application, particularly for probably many space enthusiasts in the audience, which is low-gravity electrolysis. Low-gravity electrolysis, when I talk about low-gravity electrolysis in space, I'm talking about providing oxygen to the astronauts at the space station or any other vehicle going to Mars. Let me disclose you something that you may not know. If you want to go to Mars, at this point, with the technology that NASA has developed for the ISS, which is the oxygen generation assembly, the mass that you will require to adapt that system to a Mars transfer of 6 months with a probability of loss of crew of less than 1%, that mass will be higher than just storing all the oxygen in COPVs, in propellant tanks. That gives you an idea of the level of maturity of oxygen generation systems for space applications. It is really terrible. When I think about it, I think about the IMIA machine. I will show you a picture in a second. This is the oxygen generation assembly at the ISS. It is a big wardrobe, a ton of mass, right? A ton, not in the literal sense, of course, a very significant mass and very significant variability issues. Why? Because it has a wide variety of moving parts, components, circuits, and multiphase flow management methods. The reason why we care about this is that this is a multiphase flow problem. If you want to get oxygen out of the water through electrolysis, you need to separate the bubbles from the liquid. And that is where all the centrifuges come in. Again, when I think about this system, I also think about the ENIAC machine, right? This old computer that started the computation era. At that time, they were saying that computers will take more and more space as their technology progresses. And right now, we have more computing power in our phones than we could have ever dreamed in the 1960s. So I believe there is a lot to be done in here. A lot to be done to solve the fundamental problem with low-gravity electrolysis and with space and life support systems in general, at least in terms of flow management, okay? Which is the separation of bubbles from the electrons that you can see here at the left. You have hydrogen and oxygen bubbles being generated inside an electrolyte. If you want to get this out and get the oxygen, which is the final product of your reaction, you need all this loop, a heavy, messy, and power-hungry centrifuge, and a ton of controlling equipment that is running ancillary components. Okay, so how can we make this potentially better? 2 of the ideas that we're exploring are, first of all, the magnetic buoyancy effect that they showed you before, the diamagnetic approach. Second, the magnetohydrodynamic approach. I don't know if you have seen this movie, The Hunt for Red October. It is a very classical movie about a Soviet submarine, nuclear submarine, that works through something they call the magnetohydrodynamic drive, right? It is the fundamental idea of the movie is that you can use magnetohydrodynamic or magnetic forces to propel a submarine without moving parts. Of course, nowadays, that is still not possible because the conductivity of salt water is very low. But in space, we have 2 big advantages. A, we don't have buoyancy. B, we can control the conductivity of our electrolytes. So we can really tune our system to do whatever we want. Last year, we launched this payload to test a small 2-unit half-kilogram payload inside Blue Origin's new Cephar suborbital rocket. And we wanted to test some of these low-gravity electrolysis technologies. Here's how the electrolysis technology looks like, how it works, okay? So first of all, you have a bunch of magnets surrounding a series of electrolytic cells that produce hydrogen and oxygen. And these magnets produce two effects on the cells. First, they induce a dynamic. That means that it is more or less like this magnet was a little planet attracting the bubbles from these electrons, right? It's like the same example I have shown before with the syringes. And then you have a Lorentz force. That is the magnetohydrodynamic drive in the 1990s movie, The Hunt for Red October, with Sean Connery. So we developed this payload. This is one of our core expertise. We developed micro experiments for a wide variety of platforms, orbital rockets, parabolic flights, drop towers, whatever we can or we need to use, right? Sorry, there is some, here we go. So you can see here what is happening. We are generating these little bubbles in here inside the cell, and the bubbles are being detached from the electrons. This is in sharp contrast with what would happen if the bubbles were not exposed to the effects of the magnetic force. If that wasn't the case, we would just see the bubbles growing over the electrons without phase separating. This is huge because you can induce this separation without any sort of moving parts in a fully passive system, in a fully reliable equipment, in a system that, by the way, you can reuse as much as you want, but there is almost no degradation on the magnets for this with time. So yeah, this is one technology that we're exploring right now. We are very excited about. Last year, we launched in the new Zephyr vehicle in NS23. Unfortunately, we had malfunction of the thruster of the new Zephyr, right? So the flight was aborted shortly, about 1 minute after the launch. We were there in Backhorn. It was quite unexpected, right? Then I went to Twitter, or X right now, and we saw a bunch of comments from space enthusiasts across the world. I like it particularly this one. Apparently there was a passenger on the last Blue Origin flight. Yeah, a very fun field, microgravity research, because you get to play with all these expensive and very challenging environments, right? So weather rockets, parabolic flights, drop tower campaigns, etc. I think I am over time. We can just cover half an hour. Creon, I can continue with a couple more examples, so we can go to the question time, whatever you prefer.
Why don't we go to a couple more examples if you want to do them quickly, just quick pictures of your payloads and stuff.
Okay, that's perfect. So the second example that we're covering is propellant management, right? Or the third, better say. We have a bunch of about 30 undergraduate students per semester working on rocket designs. They are developing sloshing and payloads. I mentioned before the example of the SLS, right? All that mass of liquid sloshing from side to side and inducing disturbances on the system. Turns out that the problem from a first order perspective is simple to understand, right? But very complicated to implement. So we are collecting data on the sloshing dynamics of the liquid and their effects on the dynamics of the rocket, right? We use these short rockets that have an apogee altitude of 13,000 feet. We will move to larger units in the future, but for now, this is more than enough to get and collect our data. We also work in low gravity conditions. Because there is no buoyancy in low gravity, propellants tend to get attached to corner geometries. But we have found a way to replicate that behavior on Earth here at ground level by using neutral buoyancy mixtures. The idea is not new. It was proposed by Plateau in the 19th century. But we have developed mixtures that are basically harmless. This is water, IPA, oils, and a bunch of other components. So we can play with them in the lab, and it is an excellent educational tool. Here you can see what happens with propellants in space, inside the propellant tank of a spacecraft, when they get close to the corner geometries of what we call a propellant management device, which is this wedge geometry. As I mentioned before, propellants and liquids get attached to these corner geometries because of surface tension. Creon, you mentioned before the possibility of sloshing. Yes, sloshing happens in here, but it's way harder to estimate and compute than in high gravity conditions. In particular, in CubeSat propellant tanks, as I mentioned before, stuck to the corners of your geometries, right? And that is very interesting because usually you want to get the liquid out of the tank or the gas out of the tank, but not a mixture of both. So coming out with a way to separate the liquid from the gas in this scenario is not trivial. And it requires a lot of testing, what we call technology maturation, right? From TRR 1 to 9. So we have several ideas for the reorientation and separation of propellants, particularly for CubeSats. You can see here, for instance, one of them, we apply a heat load to two-phase propellants like refrigerants, which have the best specific impulse, at least in terms of the volumetric aspect of cold gases, right? So we can apply in a heat path, we can separate gases from liquids in a propellant tank inside a CubeSat in a matter of seconds by just smartly locating the outlets of the tank. It is really fun to work with the students, right? Because I always say that microgravity research is tricky because it doesn't behave in the way that you may consider, right? Or you may think about. We would have a physical intuition for what happens on Earth, but we don't really know what is going to happen in space. Never, not even us who are studying this every day. These experiments always surprise you in one way or the other. A final application for you is thermal control. Okay, so hypersonics is a very hot field right now in terms of research and government investment, right? It is critical for Department of Defense research programs because hypersonics there is a clear technological race between China, Russia, and the US in this area, right? And Europe, but in a lesser extent, because we want to build missiles, essentially, that can overcome the defenses of our geopolitical enemies. One of the biggest challenges of hypersonics is heat transfer and thermal control. At the leading edge of these vehicles, and I say missiles when I can say also entry descent and landing vehicles, like landers, right, for the surface of Mars or Venus or whatever. In these scenarios, managing the thermal load becomes critical. Getting the heat from the leading edge to a radiator located at the back of the spacecraft or the missile is critical for the survival of that leading edge. So we're developing a technology that is magnetohydrodynamically pumped liquid metal. You can see here, we apply this magnetohydrodynamic force, the same as in the hand for Red October, to rotate and spin liquid metals across a small tube that contains them. We have a patent on this as well. This is a technology that we are foreseeing to be used for a small sat thermal control. As we progress in the next generation of small sats, they're going to use more and more power with more and more powerful thrusters and propulsion systems, right? So that requires thermal management in space. That is tricky. That is exciting too. And this technology has several advantages, among them the nearness of the liquid metal or the total absence of moving parts in this liquid metal loop, which makes it very reliable and interesting for space applications. Yeah, I think I will leave it there. And let's chat about this if you like.
All right. So let me ask a couple questions and then maybe we've got some audience questions. I'm not sure. Okay. First of all, notably absent, as you mentioned in the introduction, are sort of other than the syringes, like there's this whole question of microgravity and biology. And of course, fluid dynamics plays a role there, although there's many other things that also.
Yeah.
So ignoring that for the moment and taking the other extreme, I spent many years at NASA doing fluid dynamics work, mostly computational and visualization, but also some experimental stuff. And fundamental fluid dynamics is still a pretty active field because it's so complicated. Fluid flow in 3 dimensions and unsteady flows and all these kinds of things. And isn't there a history and a tradition and a research program of sort of fundamental microgravity fluid dynamics rather than these technology applications that you've been mostly focused on? I understand the sort of drive to focus on applied technology because of various funding and things like that. But nonetheless, have your lab or associated labs have any really interesting payloads that are investigating fundamental fluid dynamics, turbulence, combustion, that sort of thing?
Yeah, so that's a good question. So the division at NASA that takes care of that is the SMD, the Science Mission Directorate, as you probably know. And within the SMD right now, BPS is the one in charge of fundamental fluid mechanics. So the Physical Sciences Division, Space Physics Science Division. Yes, they focus on fundamental aspects of fluid mechanics in the space. And yes, there has been a ton of work done since the 60s. And there is going to be more for that. I like to focus on the applications, first of all, not just because the funding is there or not, right? I like to focus on the applications because I am an engineer and I like to solve. It turns out that by trying to solve these applications, you get to know a lot about the fundamentals of the fluids involved. For instance, in the small sat thermal control problem that I have shown you, right, the generation of gas pockets inside the propellant tank, that is a phase change problem, essentially. There were several, the zero bank boil-off experiment, for instance, at the ISS and shuttle, they were studying the same problem, but from a fundamental perspective. There are several researchers in our community that claim that the best way to study fundamental fluid physics is to focus on technology development, because you kill 2 birds with 1 strike, right? You're studying fundamental physics, yes, but you're also focusing on the final application for your system. Let me give you another very representative example. Elon Musk and SpaceX are talking about the future concept of a Starship be refueled in LEO, right? So the idea is you send two starship that eventually rendezvous in lower orbit in such a way that the second one refuels the first with a cryogenic propellant. First of all, we don't have, as of today, a way to store cryogenic propellants in space for long term, and that is a fundamental physics problem. But it's also a technological problem. We also don't have a good model for the transition of that propellant from one tank to the other through the transfer line, right? Case Western University, NASA Glenn Research Center is working on that. Professor Mohamed Kasemi is the expert in the field. It is a complicated, extremely complicated thermodynamics. What I mean with this is that, yes, fundamental fluids are important. I mean, lab does a lot of fundamental fluids with the stability of interfaces in particular, which is traditionally neglected in our sector. But we're interested in the applications because those are the ones that are going to produce something in the end, right?
Two applications questions.
Sure.
One is, the questions. One is, you alluded to sloshing several times.
Yes.
Point out it's been an issue since the earliest days of liquid fueled rockets to space. Does your work actually have any can you trace any has there been any new progress in anti-slosh technologies based on the kind of work you're doing, or are we just still with the same old, in a big tank, in the booster, we've got baffles, we've got holes in the baffles, we've got that sort of optimization. Is there anything fundamentally new that's been revealed by the kinds of work, research you're involved in and related teams, or are we still doing anti-slosh the same way we always have in big tanks?
Let me give you a two-part answer to this question. First of all, in space engineering, it is my feeling that sometimes a good enough solution is just good enough, right? The traditional sloshing methods, in particular for high gravity conditions, are very well characterized and they just work fine, right? The problem with sloshing is not as much stopping the sloshing from happening. I think that the big challenge of sloshing nowadays is characterizing the sloshing in real time. In other words, characterizing how those forces and torques applied on your spacecraft are being transferred into the dynamics of the vehicle. NASA has been traditionally reluctant to including any sort of sensor inside the propellant tanks, understandably, because the moment you have electronics inside a tank with liquid or cryogenic hydrogen, right, people start getting nervous, and that is very natural, right? But it turns out that with SLS, many of my NASA colleagues are telling me that they are experiencing many more problems than they expected with liquid sloshing inside the tanks. They haven't published this yet, but I expect a lot of research to come up based on the first SLS. In fact, I don't know this, but the thrust level that they experienced was 50% above their estimations. That was pretty funny. So yeah, there are many. Yeah, okay. There's more people saying that. Yes.
One more short one, and then we'll turn to the audience.
Sure.
There's an upcoming system, the Integrated Vehicle Fluids Management System in the United Launch Alliance. I think it's called the Vulcan, whatever their next gen rocket is that they're creating. A very interesting system, which allegedly solves a whole bunch of problems simultaneously. Problems of keeping cryogenic propellants from boiling off for weeks time instead of just a few hours like they do now or less. A lot of people don't understand this, but one of the reasons that, for instance, you always have to do your injection out of Earth orbit to deep space very quickly is because if you go around the Earth once and get 45 minutes of sun exposure, your propellants boil off. And so you have to use them quickly or lose them. And the Integrated Fluid Management System of ULA can run refrigerators, it can generate electricity, it can do hydraulics, it can do all this stuff with some very innovative technology, which we don't need to go in here. But I'm wondering is, have they tapped you and groups like yours to help them analyze this system, or are they just doing it all in-house?
I don't know who they work with because I'm not part of that effort. And also, I'm not a professor since 1 year ago. So I will reach out to them after this in case they want to chat. In any case, I am very skeptical about breakthroughs in this field, particularly in cryogenic matter, because yes, you can try to reduce the thermal to make the thermal balance more favorable, right? But in the end, you're dealing with leaks of hydrogen, which is a extremely small molecule in a tank, right? It is extremely complicated.
I think, okay, to be fair, first of all, just check it out. Integrated Vehicle Fluids Management. I think that's the buzzword, IVFM. It's United Launch Alliance. And they're not using hydrogen as the fluid. They're using kerosene. So they don't have the working fluid itself is not hydrogen or cryogenic, but the kerosene and the oxygen can run internal combustion engines, which can run generators and refrigerant systems and can run hydraulic systems. And anyway, it's a very interesting, they claim it's going to be a breakthrough, but it's not a breakthrough. It's just combining existing technologies, but they that this is going to completely change the equation for deep space things and for payload fraction as well, because you don't have to have all these separate systems. You don't have batteries, fuel cells, hydraulic systems. They're all integrated. Anyway, that's just a little thing for you. And we have a question from Luke about, Luke, why don't you ask it?
Sure. I was just wondering, I mean, it's in the weeds is a technical question, but a lot of us here have a history doing things with CubeSats, and the power budget there is really limited. So I was just wondering about the order of forces involved in your liquid metal magnetohydrodynamic heat transfer system in terms of millinewtons per kilowatt.
That is a great question. So the thing about this is that the only force that you need to move the liquid is the current. The Lorentz force arises when the current through the conductor, right, and the magnetic field interact together. So there is no added force. We have, in the examples that you have in there, we were running that liquid metal loop for with power consumption of 1 watt. And we expect to have, and the reason for that is that the liquid metal is highly conductive, right? So in order to produce a magnetohydrodynamic motion, you don't need a lot of power. That is the beauty of the approach, right? In any case, that is a sell point, yes, but I think that the key aspect there is the reliability of the problem. Instead of having a mechanical pump, you just have a liquid metal without moving parts. And that is what makes it most interesting, in my opinion.
I just want to make sure that I caught that properly. Like that heat pump that you were running was running on 1 watt?
1 watt.
Okay. And what were the temperature differentials that you were running off of here? Like how quickly were you draining like thermal energy from one side to the other?
We are running, I need to check our computations because this was just a technology demonstrator. It was a closed loop, a very small closed loop, right? Yeah. We are running right now a bigger loop with a full characterization with of those aspects. But if my memory is not failing me, in the design stage, at least in the analytical stations of the problem, we were considering a heat of 50 watts, right? And I think, I cannot tell you the exact number of grams that took. It was about 60 to 70 grams for a small sat.
How does that compare to standard heat pumps, which are used in orbit? So for some reason, they're multi-phase or whatever, they work, right?
Yeah, they use the standard heat pipes, the two-phase
heat pipes.
Because there are no, at this point, there are not high TRL mechanically pumped fluid loops, right? Because they involve so much mass and moving parts that the reliability is a big concern.
I beg to differ with you. We have heat pipes on our spacecraft that are completely sealed with no moving parts whatsoever and no power required, except only moving part is the working fluid that's in.
Yeah, but not in CubeSats. If you check the technology review for CubeSats, the state of the art of the technology
pipes, there are heat pipes that are this big, so you can put because you won.
Yeah, but these are not mechanically pumped fluid loops, right?
No, they're passive.
Yeah, but you need to compare apples with apples, right?
Fair enough.
The technology for pump loops is intrinsically different and has different applications. So yeah, in that sense, we are overcoming them by a factor of 2 in terms of mass. So this is, at least according to estimations, this is a very low TRL technology. So that means that we need to go through the TRL 3 to 6 validation to get hard evidence on everything. But the analytical estimations and the preliminary results indicate we can get half the mass for the same amount of heat transfer from one place to the other. In particularly with copper conductors, which are extremely heavy. They work very well for short distances, but as soon as you try to get heat from more than 10, 20 centimeters, they're extremely massive. And with heat pipes, the problem is localize hot spots, vaporize the internal refrigerant or two-phase liquid faster than you can bring it to the other side of the.
So out of curiosity, because I do work for a satellite company, would you be interested in maybe discussing this with our thermal team? Because we might be willing to fly something like this more rapidly than you might find through a NASA program, because we have desires to move heat and we don't really want a lot of mass and power to be thrown at that problem or complexity. And right now we use heat straps and passive heat pipes. And one of our payloads needs cryogenic cooling. It uses a solid state, not a solid state, a cryo cooler. Again, it's a completely sealed unit, but whatever. I'm interested in having our team look at this and see if there's any possible way we could fly a prototype or at least do some ground tests on it, something like that. Okay.
Absolutely.
I don't see any other questions in the chat. And I don't see very many people, John or Emmanuel or Allison. Does anybody have any?
I always have my foresight questions.
What
Yeah,
are your
thanks.
side questions, Allison? Why don't you ask yours?
Yes, the greatest pleasure. Thanks a lot. That was really exciting. And I think definitely a lot of new information for me, at least. Yeah, I'm always learning a ton at these seminars. But from a foresight point of view, like two things are at least always like pretty relevant for our groups. One of them is the more kind of like speculative question, and people don't very much like to get, but it's really interesting to listen to, which is if everything goes well, where do you see this technology or like this progress really being in 5 years? Let's say you can make like continued progress. What's kind of like a nice carrot that people could be looking forward to if everything goes well?
So you have given me 5 years. So I'm going to focus on something that is going to be flying in 5 years. Okay, so I think that the market for propelled CubeSats and for formation flying in CubeSat is going to expand drastically in the coming years, right? That is almost a necessity. We have a CubeSat mission here, Visors, led by Professor Glenn Livesey, that deals with this sort of problems. All those systems require propelled CubeSats. It turns out that propulsion systems for CubeSats, as of today, are highly inefficient and unreliable. And if not, think of what happened with lunar flashlight, right? And all the clogging issues that they had with the propellant lines inside their system. So I think that in 5 years, I think that the technology that is going to be probably, or that I hope to see flying sooner, is the propellant positioning within CubeSats using cold gas propulsion systems. That is one. And then with respect to the heat loop device, that may take a bit longer because we need to reach the point where we actually need heat to balance the thermal loads acting on the system. So that is going to be maybe a 10-year problem, but it's going to happen eventually. And we're going to see that flying. These and other technologies are going to pop up eventually. So yeah, I don't think it's all speculative. If you ask me about 50 years from now, I will tell you we need a new oxygen generation system for space applications, for going to Mars in particular.
I love that you went all the way out there. That would be my next question. And is there like, are there any obstacles or something that you would like other people, let's say, some junior folks that are just entering the space to take on, where basically, if you could request help with something that other people could focus on to advance your work, what would that be?
This is a kind of petition for me. So the thing, fluid mechanics, fundamental biology in space are extremely underfunded at NASA right now. It happens year after year with the presidential budget. But if you don't master fundamental fluid mechanics and fundamental biology in space, there are a ton of problems that you are postponing and that are going to cost you way more money down the road. And we have a joke in the ISCSR community because let's say that one of the older fluid mechanicists in the community says that I am the youngest fluid mechanicist in the US right now, working in academia at least, and that he's the second youngest, right? And he's 65. So we have a problem here. We have a generational break since the shuttle accident in 2000. NASA has not funded fundamental physics, or the Congress has not funded fundamental physics and biology in space. And those two fields are going to be critical down the road for a wide variety of space technologies and space exploration. So if you ask me, if I think we need some sort of help in this field, absolutely. But beyond everything, we need better funding at the government level to make this work.
All right.
Yeah, well,
we are at the last minute or so. And Allison, thank you so much for you and your staff for organizing this as usual. And thanks to Nate and Lydia and all these people and you and Alvaro, of course, thanks to you. This is pretty cool. And I look forward to our next round.
Pleasure meeting you all, and thanks for being a pleasure.
And this, by the way, Allison, correct me if I'm wrong, this will eventually show up on YouTube if you give permission, right?
Of course.
Yes, will show up on YouTube. And one thing that I guess I should also be pointing out, that people have been asking, is if you want to join us in person, Vision Weekend is coming up. And that's our annual member festival across San Francisco and France. So if you're interested, go to our website, Vision Weekend. We have a France edition and we have a US edition from November 17 to 19 and December 1st to 3rd. And there's a ton of speakers in energy and space for both of these events and categories there, including Cleon. Really excited to have you there. And yeah, please do consider joining.
Bye, everybody.
All right, everyone.
Thanks for coming.
Have a good one. Bye-bye.